Okay, let's consider one more example on angular momentum. And in this case, we have a stick that is staying still, and the length of the stick is 2 meters, and it weighs 10 kilograms. There's a particle, or let's say it's 30 kilograms. There's a particle, and this is the center of mass. In fact, there's a bullet that is coming towards the stick, going to hit the end of one, going to hit one of the ends, and the mass of this particle is 10 grams, and the velocity by which it's coming is 300 meters per second. Okay, so what happens? This guy comes and lodges itself inside the meter stick, and then the meter stick and the combined meter stick combined with the bullet starts to move. I'm sorry, this is such a bad. Assume that's a stick, not the meter stick, a stick, and you have this bullet here. So this guy is going to move forward and also going to go in circle. So this is going to be the final movement of the whole system. Why is it so? We'll understand. First of all, what's happening here? Is there any external force acting on the system? There's no external force acting on the system. Is there any external torque acting on the system? There's no external torque acting on the system. Is energy conserved? No, energy is not conserved because it's an inelastic collision. But using conservation of angular momentum and conservation of linear momentum, we are being asked to calculate the velocity by which the center of mass of this whole thing will move, and the angular velocity by which this thing is going to rotate about the center of mass. So it will become more clear as we proceed. So let's talk about conservation of momentum. What is the initial momentum of the system? It's 0.01 multiplied by 300, and that gives us 3 kilograms meters per second. And what is going to be the final momentum of the system? Well, it's 30 kilograms. So this pi, and pf is going to be, let's call this x-axis, 30 multiplied by v. So it's 30v. Why is it 30v? Because we know that if v is the velocity of center of mass, then the momentum of the system will be just mass of the system multiplied by v. We already have discussed that m, which is the total mass of the system, multiplied by v of COM, is nothing but the total P of the system. So the total P of this combined system is going to be the mass of the system, which is going to be 30.01, but let's sort of discard 0.01 in comparison to 30, times V. So M is 30.01, but let's just write 30, and VCOM is what we are trying to calculate, so V here. So that is the final momentum, and from here we can calculate that 30V is nothing but 3, because momentum should stay conserved no matter what happens, unless there are no external forces. So that gives us 0.1 kilograms meters per second. Alright, so this is the velocity of the center of mass by which it moves. Also, the whole thing is moving about the center of mass in an angular way. Why is that happening? Because initially about the center of mass, this guy had an angular momentum. You see, we calculated the angular momentum of any object moving with a velocity v and has mass m at radius r to be equal to mvr. From one of the lectures we calculated that. So this particle has some angular momentum about the center of mass, and which is 0.01 multiplied by 300 multiplied by 1, which is nothing but 3. 3, and the units will be units for I omega, whatever is the unit for I omega. And the final angular momentum of this mass will be what? Well, again, the final angular momentum will be calculated about center of mass. So about center of mass, we know I is given as, this is I final. So I final is given as ml square over 12, where L is the length of the stick, and that turns out to be m is 30 times length is L is 2, so it becomes 4 divided by 12, and that gives us 10. So this is I final. So what is L final? L final is I omega, or IF omega F, which is going to be, well, let's just call it omega only, which is going to be 10 times omega. Now because the angular momentum will remain constant, we have 10 omega equals 3, and omega comes out to be 3 divided by 10, or 0.3 radians per second. So the moral of the story is that angular momentum, which is always calculated with respect to a point, and in this case about the center of mass, there was some value of angular momentum for this bullet about the center of mass, which remained conserved. And the way it was remained conserved was that the stick started moving angularly about the center of mass, and the way the linear momentum remained conserved was that the center of mass started moving linearly, or in a straight line, such that the momentum also stayed conserved. So this is why this motion happened like this, to make sure both angular momentum and linear momentum stayed constant.